This presentation relates to trusses, and it's the first one about this particular technique to build with several elements, especially with steel. The contents are as follows. As an introduction, I want to explain what is a truss. We have a truss when we have an assembly of elements that are linear, right? The ones that we are looking here, and those elements are part of a system formed by several triangles. Usually, the elements are linear. Usually, we work with triangles, but not always. And the triangles are very simple shape. Pyramids were made as a triangle because you have not so much weight in the top part of the structure and a strong base. Also, they are very resistant to forces and are very stable. Well, in a truss, forces are supposed to be divided. If I apply a force in a truss, this force will be divided in several forces that will be smaller and therefore will be able to support more weight. Normally, we apply the forces not in the member, but usually in one of the joints, as here. Let me clean everything here and continues. Truss terminology is very important and you need to learn each one of the members. As we can look here, we have a top chord in red color, diagonals elements that are in green color, vertical elements in white colors, and finally the bottom chord in yellow color. The joint is the place where all the elements are put together like a node, and the span, as you know, is the total length of this material. When members are the vertical and diagonal members, and chords are the top and bottom members of the truss. We have several truss types, and you need to learn all of them. You need to be able to identify a photo with a Pratt, a Hope, a K-truss, Warren, etc., etc. Look the difference between them, how the chords can come, for example, from the center, inferior or bottom part to the left or to the right, or it can instead start from the inferior part to the left and right in this different way. A very simple truss is the Warren that is made by triangles. And you need to understand and choose which kind of truss you would like to use in your projects. And you will learn in this class to calculate that truss, especially for one of the methods. That is very important to learn, and that is easy because it's graphical to do by the architects, as we are. When we use trusses, the truss provides like deep with less material. When you have a beam, you have a lot of material in the whole element. Instead, in the truss, you have less material in the areas that you don't need it. You can use small pieces, it's light open, and there are many shapes that are possible. As you know, the best beam that we can have, the best section of a beam that we can have Usually it's a section like an I-beam where we have a lot of material in the top area and a lot of material in the bottom area, and we don't have so much material in the center. When we divide the section in parts, we can look that in the center there is less material than the material that we will have in the rest of the areas that are located here in the top and here in the bottom. Why that happens? Because when we put a weight in that section, like a load, we know that in this area, we will have tension, a lot of tension, and the nearest to the end, the biggest is the tension. And in this area at the bottom, we will have a lot of compression because the beam will tend to deform like this. Compression there and tension there. That's the reason why we need more material. Well, with a truss that happens, we have a cord, and the cord in the superior part here in yellow, in section have more material than the web members. Well, when I do a cut and a section of this particular truss, it will be something like this. I will have material here in the top and in the bottom. Usually those elements could be something like two elements like that. And similar to the I-beam, we have less material in the center. You see? Therefore, it's working even better than an I-beam and can resist a lot of a very big span in comparison with a beam using less material. And that is a very big advantage of this particular way to build. Let me clear everything. Well, we can have multi-panel trusses, for example, like the Sainsbury Centre in Norwich in England, designed by Foster and Partners, where we have elements that form all these triangles and create a three-dimensional element that is able to support not only the span, but also serve as the columns of the building. We have Warren trusses in the Central Georges Pompidou here, and we have 3 hinges trusses in the Waterloo terminal for channel trains that communicate England with France. And this is the Stadium Homebush in Sydney, Australia, where we have very big span. Well, they are very versatile, and they are convenient in many cases, but sometimes they are not convenient. And one of the problems of trusses is that we have a lot of labor in the joints. The appearance can be a little bit fuzzy for some people because beams are more clear in lines, more clean in lines. And it's not convenient when we have heavy loads. We need more lateral support than any other materials. Well, the trusses will tend to bend laterally. They are not suitable for heavy loads, and you cannot hang weights in structures because they resist a big span, but the loads that are resisting are not as strong. The real applications of trusses in domestic roofing, when we have the space, when we have long span flooring, when we are using bracing systems that usually are big trusses, etc. The trusses have realistic shapes, and there is a span to deep radio that is normally between 5 to 10. I mean, the length of the truss, the span will be 10 when the deepness of how tall the truss is 5. This is at least twice as deep as a similar beam. Well, you need a lot of deepness in order to make a truss. The deep of trusses can sweep roof roof that have a pitch, and that is something convenient. Well, the typical proportion of a beam is the span divided by 20. When we speak about concrete, we can have the span divided by 10. I mean, if you are doing a concrete beam and you are doing a section in your design classes, you need to understand that if this beam has a span of 10, when you do the section of this beam, the height or depth of the beam could be 1 to 10. With some types of wood, with steel, it can be a 1 to 20. But when you have trusses, because you don't have material here in the middle, the span increase. But also increase the depth of this height that the element have. Well, in a truss, we can have a span of 10 when you have a deepness of 1, but it's difficult to arrive to the typical proportions of 120 of some materials, such as wood or steel. Well, I hope this is clear because this is very important for your design classes. Next, we have several methods to analyze trusses, and the methods are joint method, section method, and graphical method. I will start with the joint method. This joint method, we need to isolate a joint. Well, we will imagine that we have a joint that is by itself. For example, we'll isolate the joint A. Well, I have the joint A with 1, 2, 3 members plus the joint that is here. And I will start to calculate what are the different loads that each one of those members are supporting. Usually when we do that, we try to look the place that is easy. And the place that is easy to do this type of calculations is in a place, let me go back, is in a place where we already have some answers. For example, here in this point, we know how much is the reaction F, because if not, we will not be able to resolve this element that is similar to a beam. And we have two forces, force 1 that is the member FA, and force 2 that is the member FP that we need to calculate. Well, it's not that difficult because we can make a summatory of vectors, and with trigonometry, we will be able to calculate F is already there. Well, we'll be able to calculate how much is FE, that is this vector for 1, and how much is the other vector that is FA. That is this vector in particular. Well, it will be possible with trigonometry to work. After we know this joint and we resolve as an independent member, we can go to the one there and the one over there. We can move, and we can resolve only one joint at a time in general. Well, this method requires a lot of time, it's a little bit complicated, and obviously you need to have a good knowledge of maths. Well, as we look here, we can deal with inclined forces. For example, if I go to this point, AF, I will arrive to the conclusion that we can work with trigonometry and find what are the vertical and horizontal forces of this particular diagram. Well, I can substitute the original force that is a reaction as a force that is pushing down the particular truss that we're calculating, the particular joint A. and I can calculate how much are A, B, and AE using trigonometry, as you can look here, where vertically it will be AF plus AA multiplied by the sinus of A, the angle alpha, and horizontally something similar, but using AB plus AE multiplied by the cosine of the angle alpha. Second method is a little bit similar. Instead to isolate one joint, we cut the beam in the place that we want to analyze. Imagine that a particular member is supporting more weight and we want to know which member is supporting more weight. If we suppose which one is, we can just cut, like we did with the beam before. We cut and we look what happens at the left or what happens at the right. Well, this is similar. We cut the beam with this yellow line, and when we cut, we see that in the right side there is T1, T2, and T3, three forces, and we can try to put all those forces together and using maths try to find which one of them is working. The advantage is that it will be very useful to use to find the maximum core forces in long trusses. When we have a truss that is very long, imagine I will need to start to calculate this truss by this point that will be like the joint A, and move to B, move to C, to D, and do all these calculations to arrive finally to the one that I want to calculate, for example, that is this superior member. And that will take a lot of time. Well, both methods are not easy if you don't have a good comprehension of mathematics. Well, many of you will be able to do it and work with them, but I do prefer the graphical method. And the graphical method is a method that allows you to calculate all this information very easily. In order to work with the graphic method, we need to use the bold notation and draw what is called a Maxwell diagram. And that will allow us to calculate exactly what is the force that each one of the elements is supporting. We can have a quick assessment when we have parallel trusses, and we can just try to calculate some elements called like the bending moment in the beam and use some formulas to calculate it. When we have a pitched trusses, we can work with maximum forces that will be there, and usually there are in the supports, and that make a little bit of sense. I mean, if this particular truss is supporting weights as we want in the nodes that are there, because you have a roof, for example, in the top of this truss, well, all those trusses will be, all those forces will be transmitted, and all are linears, all the members are in compression or in tension, will be transmitted to this point, because that is the point where you have the columns or reactions that are supporting this truss. Well, the member in red and the member in green will be the ones that will be supporting more weight, and we can calculate the forces using those formulas. When we have a truss that is shallow, we will have large forces because it's not as high as a truss. It's like a beam. We want the beam to be high in order to support more weight. Let me clean this. Well, there are many types of trusses that are very interesting, and there are trusses made in places like in Vermont that they are made out of wood, and they are able to support very well the weight of cars. There are combinations of trusses. There are trusses that are more complex, like the Quebec Bridge and the Tacoma Narrow Bridge, that the truss is used only for the deck, but is supported by cables. And well, we all know about the failure of the Tacoma Bridge. And this concludes this presentation.